Okay, so the next topic in sequences and series is factorial. So more often than not, we will be using this symbol. We will look at sequences and later on series that involve factorial. But what is that? What is the factorial? Well, the factorial, which is denoted and with an exclamation sign, looks like an excited number, but it's not an excited number like 3. Whoa, right? Well, we could say these numbers get excitingly big because when you perform these calculations, well, what we do to simplify these numbers is multiply all the integers below n. For example, 3 factorial, 3 times 2 times 1 equals 6. And then the next factorial, 4 factorial, 24. See how big they get? Just for 8 factorial is already a 5-digit number. It's getting big really fast, right? And well, the way we simplify these factorials, or rather the way we represent, it could be in more than one single way. For example, I'm going to take as an example 6 factorial. Let me write it down again. Let me write it down here. 6 factorial equals to 6 times 5 times 4 times 3 times 2 times 1. Okay, do we all agree that this is all these numbers right here? 5, from 5 to 1. Isn't this the same as 5 factorial? Mm-hmm. So we could rewrite 6 factorial as 6 times 5 factorial. That's another way to write it down. Now, another way to write this down is, okay, group the last 4 digits, and isn't this 4 factorial? Because that's 4 times 3 times 2 times 1. That's the same as 4 factorial. So another way to rewrite this is 6 factorial equals 6 times 5 times 4 factorial. Well, which one are we going to use? Well, it will depend on the need. And to see this in action, let's look at some examples here. One important note is, well, both factorials of 1 and 0 are equal to 1. All right? And, well, so let's simplify these expressions involving radicals. So the idea is, when we work with these factorial expressions, is to simplify them in a way that no more factorials are left on the expressions. And what we do is to work on the largest of the factorials. So between 9 and 7, 9 factorial and 7 factorial, which one is largest? So we're going to expand the 9 factorial. So that is, well, we could do the following: 9 times 8 times 7 times 6 times 5 times ... and divide by 7 factorial. But do we really need to expand too many numbers? Not really. So we could do 7 factorial, so we can cancel with this 7 factorial. And cancel, our final answer is a 9 times 8, which equals 72. Alright? Let's have a look at the next one. Letter B, 12 factorial divided by 3 factorial times 10 factorial. Well, the 3 factorial in the denominator is fine because that's 3 times 2 times 1, which is 6. No big deal. However, the simplification would go rather with the largest of them, in this case the 12 factorial and the 10 factorial. So in this case, we would like to get rid of the 10 factorial by expanding the 12 factorial the following way: 12 times 11 times 10, and because in this case this 10 matches the one in the denominator, call that a factorial. And this 3 factorial, we can call it a 6 already, that's fine. And in this case, cancel the 10 factorials, and we can divide out the 12 with the 6. That's a 2, that's a 1. We would be left with 2 times 11, which equals 22. Okay? Well, so this is with numbers. What about with variables? Because we are going to look with limits of sequence that contain factorial. So, and again, the usual focus on the largest of the factorials. So, the largest of the factorials in this case is n plus 1 as opposed to n. So in this case, what I'm going to do is n plus 1, open and close parentheses, and then 1 below, so n plus 1 minus 1 would be n, which actually happens to be the same as n factorial. Cancel, cancel, n plus 1. All right? For instance, 2 plus, 2n minus 3 factorial, 2n plus 3 factorial. All right? Which of the two factorials is the smallest? I mean the largest. The bottom. So we're going to expand in this case towards the largest in this case. Well, 2n plus 3, 1 less, that would be 2n plus 2, 2n plus 1. Yes, this one is going to take more factors actually. 2n. And you know what? Let me change this to negative 1 because I'm going to run out of space. 2n and 2n plus, or rather 2n minus 1. Call this the factorial. And just cancel the factorials. You will be left only with 1, 2, 3 factors below, all right, in the denominator. So that's how we deal with factorials. Expanding over the largest of the factorials, as many factors as we need until we find the one that matches the one that we want to cancel it with. Okay? Alright, so what we have done for now is look at pretty much the algebra, the arithmetics of sequences. And you know, as usual, every time you learn like a new topic in mathematics, you learn the arithmetics, the algebra, and then the calculus of it. So now let's start looking at the calculus of sequences. And well, the first topic in calculus, of course, is limits. So we will determine whether a sequence converges or diverges by finding its limit at infinity, because these are infinite sequences. So this sequence may just blow up to infinity, or they may converge to a value, to a finite value that could be 0. I mean, any finite number, irrational, rational, doesn't matter as long as it's not infinity. And all we do is set up this as a limit problem. If necessary, use the L'Hopital's rule, every technique that you may find in handy. All right. So let's determine whether the infinite sequences here converge or diverge. Well, so let's write this as a limit of 4 minus 1 over 5 to the n as n approaches infinity. Well, where is that going to go to? 0. Okay, so this means 4 minus 0 equals 4. What does that mean? Converges. The sequence converges. All right, sequence converges.
Would it be 4 minus 1?
4 minus.
Oh, never mind. I thought it was
Yeah.
0.
Oh, yeah, I see what you mean. No, yes, it's 4 minus 0 and it's 4. So, okay, the square root of n. Let's write it down simply as a limit expression. That's a limit n approaches infinity of the square root of n. And well, what is that limit equal to?
Infinity.
This means diverges. Oh, let's look at this one. Letter C, negative 1 to the n. All right, let's set it up as a limit first. Negative 1 to the n as n approaches infinity. All right, what about this one? Oh, negative 1 to the n. 0. Okay.
Did you do the natural log of it?
Do the natural log and treat it like an L'Hopital's rule. Could be. However, let's make this a lot simpler than that. Okay, let's look at what this sequence is doing. Okay, when n equals to 1, what is that equal to? Negative 1. What happens when n equals to 2? N equals to 3? N equals to 4? And so on. It's just oscillating between negative 1 and 1. So, because in this case, because of the oscillation, it's neither at 1 or negative 1. Well, this is simply, on the one hand, first of all, in the limit language, the limit does not exist. Yes, technically it's the same when the limit is infinity. There's no infinity, but when it comes to a limit that the result is infinity, it has a different nature of whether it's getting big positively or big negatively. All right, and in this case, there's an oscillation. It's neither one place or the other. All right, so DNE, but still the conclusion will be the same. Diverges. All right, let's look at the next one. Limit n approaches infinity. 3n squared plus n minus 1. 6n squared plus n plus 1. Okay? Yes?
Is it the same with like sine?
Exactly. Exactly, does not exist for sine at infinity because it also oscillates between negative 1 and 1. That is true. Okay, so this limit, at this point, use whatever is easiest for you. Of course, in Calc, when you went through the painful process, painful in the sense that you had to write like a lot, by dividing every single term by the highest power of n that is seen in here, and then just see how most of the terms go to 0. But the other way is because the easiest one in this case, just go with the ratio of the leading coefficients, because in this case the degrees of both numerator and denominator are the same, so that's only 3/6 or 1/2, which means converges. All right. Let's look at the next one. Yes, and I left like a lot of space here because I used to do it like the long way, but yes, I think the concept is there, right? I think at this point we're all good. Okay, letter E, limit 2 to the n over 5 to the n and factorial. As n approaches infinity, not n factorial. What about this one? It's 0. I agree with the 0, but why is it a 0? It's a decreasing function. Well, in this case, clearly the denominator is going to get bigger than in the denominator. Well, when we divide by a larger number for larger values, well, the denominator gets really big, and when we compute that, it's going to end up being just 0. And in this case, converges. Well, actually, let's go a little bit further and explain why. Well, so keep in mind that this resembles the following function. 2 to the n over 5 to the n is the same as saying 2/5, the whole thing to the n power. This is some sort of an exponential function, f of x, or yes, f of x equals a to the n, where in this case, for a between 0, not equal to 0, and 1, it's increasing. But otherwise, if a is greater than 1, alright, greater than 1, actually decreases. And increases. And the graphs look something like this, and otherwise something like that. And that's from either intermediate algebra or that chapter in logarithmic and exponential functions from pre-calculus or college algebra. So, so that's pretty much the reason. But the other way is to just say that the denominator just grows faster than the numerator. And that also remember the growth rate from L'Hopital's rule. But well, in that case we compare polynomials with logarithms and exponentials and power of an x function to another function. Well, in this case they're both exponential, so they're in a way at the same level of growth. However, what makes this limit be 0 is the fact that the largest exponential is in the denominator. Now, is it the same for the next one? For letter F? What about it? This one is an increasing function instead, right? When we compare to these two right here. And well, the limit will be infinity and diverges. All right.